Hello, I have to record the lecture, so let me check if my setup is correct. Okay, welcome to lecture one of the Information Theory course. I am Sachin, PhD student in the Indian Institute of Science, and I'll be a course instructor. This is the first time I'm teaching this course, this particular course, so uh, things might not be things might not flow very smoothly, but we'll cover all the topics that need to be covered. Right, today's lecture will be a bit short. It will only be an introductory session, and I don't know how long it will take. So I haven't figured out how much material I can cover in. one lecture. So this will be kind of an experimental lecture, you could say. Next time I'll have a better idea of how much material I can cover at once. Okay, so today it's introduction. So in the first thing you need to know when you're studying information theory is what information is and in what sense we are talking about information. So of course the English meaning of the word is not exactly applicable to our uh, applications. We can't directly take it as it means, but there is a bit of correlation. So any type of data would be called information, but we need some kind of definition if you want to work with it mathematically. So, for example, in physics, when you're talking about speed, then you would have an intuitive notion of what speed is, but you can't work with the intuitive notion. You need some type of definition that tells you what exactly it is, how you can measure it, and how it is related to other quantities. So, similarly, here information is defined in a particular way, and if something that you want to talk about, if you think that is some type of information, then it will have to fit this type of particular model. So we will deal with that type of information which fits in our model, and we'll give a definition. Right now, I'll give just an intuitive definition. I'll make it precise later. So the way we will think about information is the reduction in uncertainty. Again, even in this statement, even in this definition, first I'll have to tell what uncertainty is, but we'll come to that later. But for a low level or for a high level example, suppose there is a tournament that is, uh, let's say there is a cricket tournament that is going on, and uh, a lot of rounds have already occurred, lots of matches have occurred, and you are finally at the quarterfinal stage. So there you would have, let's say, 8 teams, and they will play against each other. Four of those will go to semi-finals. They will play against each other, and two will go to the finals. And finally, there will be one winner. He'll be declared as the champion. That team will be the championship team. So initially, before the quarterfinals or any of the matches occur, you'll have certain a certain sense about who might be the winner. So it could be any one of the 8 teams, but you don't know who exactly is going to win before the matches occur. So that is so you would say there is some uncertainty in the outcome of the matches. That uncertainty depends on the number of teams there are. So if at a particular stage, let's say there at the quarterfinal stage, there are 8 teams left. So there is some amount of uncertainty about the winner. After all the quarterfinal matches are over, there will only be four teams left. So now you are more sure about who the winner is than you were earlier because four of the teams have been eliminated. So you have reduced the uncertainty in the outcome of the matches. Next, after another round, after the semifinals are over, there will only be two teams left. So the winner has to be one of these two teams. Now you are much more certain about the winner of the tournament than you were earlier before. So there has been a reduction in uncertainty in this process, and this particular reduction in uncertainty is called information. So we will deal with information in this sense. And information theory will deal with problems regarding information. And since I am an ECE student, I'll be teaching this from the perspective of a communication engineer. So the applications or the things that I want to achieve are different from someone else, say in computer science, who might also be using information theory, or someone who is using it in statistical inference. So for communication, the main goal of information theory is to answer two questions. The first question is, what is the ultimate limit of data compression? So when we have certain information, let's say we have some data that we want to store, or let's say you have a novel, you will have to store the novel on your computer. You will do it. You can't directly store the letters in a computer, right? The computer only takes binary values. So you can only store binary values in the computer. And if you might have studied in computer science that letters have an ASCII combination, so they're assigned some sequence of binary digits, and when you press an A key, what is actually being sent or stored will be that particular ASCII code word. So whatever information you want to store, you will convert it into a form that is suitable for storage. And most of the time, it will be a sequence of bits. So if it's from a novel, you would take the letters, and for each letter, you would give a particular sequence of binary numbers, and you would say that sequence of bits will represent that letter. So, for example, if you want to represent A, B, C, and D, you could say, I will say 0000 is A, 0001 is B, 0010 is C, and so on. So with four bits, each of them can be either a 0 or 1. So you'll have 2 power 16 combinations. So if you had 5 bits, you would have, sorry, not 2 power 16, 2 power 4. If you had 5 bits, you would have 2 power 5 combinations, which is 32. And using 32 different combinations, you can pick any 26 of them and represent all 26 of your letters. So when you are storing a book, you will map from the letters in each word to these binary sequences and store these sequences on your computer. But that's not the only way you could have done this. You could, for example, say A is 0, B is 1, C is 1 0, D is 1 1. You could save bits by representing them with variable length. And this might, of course, if you store this instead of this, you're saving a lot of bits. You're storing the same amount of information. So whenever you see five zeros here, you will say that it is A. But in this system, a single zero is enough to make sure, enough to tell you that you're storing A. So you can use a different coding to compress the data that you have. That is, you can represent the information you have with lesser number of bits. So that would be data compression. That you would see in huh, yeah. So any arbitrary mapping can't be a code. That is also one point, one aspect. This is just some example that I cooked up. That's all. This is not how you would do it, but there is a method to do compression also, and that method will make sure that whenever you have a sequence, say 10011 something like this, it will make sure that there is only one way of interpreting, parsing that sequence. So from left to right, if you go, you'll only have one method of uh, dividing it. So you will be able to tell whether you actually sent something representing 100 or you actually sent 1000. I'll come back to that later. So we will see that in later parts of the course, but in this lecture also later I'll give you an example. So you have to make sure that you can properly tell what it is your story. That is one aspect. Second aspect is, so of course randomly you can't assign like this, but you can still do variable length coding instead of doing fixed length like this. So where you are using 5 bits, and there will be some advantages. Okay, so suppose you are storing a novel, right? What is the probability that you will encounter a Z? So how many times Z would occur in a novel? It will be much less than A, right? So when you're assigning these code words to them, it would be better to assign smaller length code words to the letter A and larger length code words to the letter Z. So A you could represent with 0, B you could represent with say something like 1111. Then since the probability that A will occur is higher, that is you have more number of A in any book than you would have zero, Z, which is true for most books. Then if you follow a pattern like this, then you'll be in the end on average storing lesser number of bits. So that is how you get compression. We'll see how exactly we do that later. This is first lecture, so I'm just giving you an overview of what we'll be doing. So that's one question that we want to know. Given certain information that we want to store, what is the least or the smallest amount of bits, or you could have some other measure, nats, or you could have something else to measure the smallest unit. But in the end, what is the least amount of data you need to store to actually store some particular information in the source side? So this is what you use. Uh, so compression you would have seen, right? WinZip and all, WinRAR. So they'll do compression there, and then audio compression is also done. There will be codecs, right? Uh, for when you're streaming music, they won't send you the exact bit stream. So they'll compress it and send it to you. So most of the places when you're trying to store or transmit something, you try to compress so that you can save on the uh, data that you are using. Even images, JPEG, it's a compression standard. So you won't, when you take a photograph, you won't be storing all the pixels in the photograph. You will be compressing it and storing much lesser. But you will make sure that you can reconstruct it anytime you want to view it with a good resolution. So that's one question. And this question, the answer to this question will depend on a quantity called entropy, denoted by H. The second question that you would be interested in communication is this is called the ultimate limit of or ultimate rate of communication. That is, so now I am talking to you through this Google Meet where my voice is being converted to bits and the stream of bits is encoded further, and then it is being transmitted over the air through Airtel towers or whatever towers there are, or through cables, and then it is reaching you who are far away from me. And in the process, the channel will add a lot of noise. So this question will tell you at how much rate you can send or receive information over a channel. And that will depend on the noise that will be present in the channel, the signal strength that you are using to send the information, all of that. But in an information theoretic sense, it will depend mainly on a quantity called the capacity of the channel. So when we say ultimate rate of communication, we just don't mean any type of communication. It should be reliable communication. That is, by reliable communication, what we means is I should be able to send something. The sender should be able to send something to the receiver such that uh, the probability that the receiver will get some wrong information or a wrong message should be below any threshold that he wants. So he can pick a threshold. Yeah, what is it? Yeah. So channel would be the medium through which you are doing communication. For example, if you're doing wireless communication, you're sending radio waves through air, right? So then the air will be your channel. Of course, there might be obstructions. So there will be buildings in between. There's the earth which will do some reflection. There is a stratosphere which will do some reflection. So depending on the frequency and what type of communication you're doing, all this will be different, right? So when you send through a wireless medium, through air, it will be a wireless channel. And there will be models for each channel. When you are talking through telephone, right? So your words are being converted into signals. I'll explain what a signal is. Signal is nothing but some uh, how do I explain what a signal is? Signal, you could say it's any type of data that you're trying to send or process for like an electrical signal. So you talk through your, have you seen landline phones? You talk through the phone, that will be, your voice will be going through a microphone, and then based on the pressure, right, different words and sounds will have different air pressure. It will cause different air waves, and that will actually be converted in your microphone into electric uh, current values, right? Depending on different pressure. So if you're and there will be also loudness, right? Depending on all that, you the different words or sounds that you make are converted into different values of voltage or current. So that voltage or current would be your signal. No, it doesn't have to physically be there. When we talk of channel, it will be a model. So, but at the end of the day, you are trying to model some real physical stuff, right? So there will be something physical also. But when we deal with communication, we will abstract out all the irrelevant details and only work with particular models. Uh, yeah, I am using it interchangeably, but when you say a channel, there will be a exact definition of what a channel is also. That right now we don't need it. When we need it, I'll tell you. So all these, so all these things you can't see when you are thinking about them. It's okay to think loosely. You don't have to think of the precise definitions. But when you are trying to make some statements about them, right, some theorems or some results about them, then you'll have to model everything and explain exactly what those things are. At that time, what a channel is will be very specific. It won't be any random thing. But for now, just to understand, you can think of channel as anything that through which you do communication or on which you're storing information. For example, a DVD would also be a channel because I can store it at some point of time and later someone else might watch the DVD. So at that time they will retrieve it. So your channel is actually the DVD or a pen drive. Yeah, signal is the data that you're trying to communicate or store. So there are things that try to uh, represent some physical quantities usually. For example, the temperature, you might want to temperature is just a measure of how hot or cold something is. So you would have a certain value for the temperature, and that could be a signal value. So to learn more about this signals, you could check out signals and systems course. And communication channels and all a lot more details will be taught in a communication systems course. But for our treatment of information theory, whenever I mention something, Mostly, I will give a precise definition of what we are talking about. Okay. So, in an abstract sense, these are the two main questions that we are interested. So, given some information, uh, how can we store it so that we are incurring the minimum storage cost? We are compressing it to as small a quantity as possible. And given channel, at what rate can we do communication? How many bits can I send at a time for channel use so that the entire thing doesn't get corrupted and you are still able to recover whatever data you need. In other branches, you will have you might still use information theory. You might use it in statistical physics, uh, mostly thermodynamics. So computer scientists can also use information theory in a problem called Kolmogorov complexity. So I haven't studied these problems myself, but uh, Kolmogorov complexity is, I guess, it's a way of checking uh, to do some task. What's the shortest program you can write, or something like that? So a computer program, what's the smallest code you could write to get something done? It's a problem of that type, and there you could use it. And statistical inference. So there's a principle called Occam's razor. Says that if there are multiple explanations for something or multiple possibilities for something, then most likely possibility to occur is most like the possibility is the simplest one, some principle like that. So of course that's very vague, and information theory helps you to give a more concrete and more rigorous version of this principle, and you can use it in probability and statistics, in hypothesis testing. So for example, you could have a fire extinguisher, and uh, when smoke is generated, some kind of signal will be triggered. So that will be triggered based on some kind of physical phenomena. But at the end, you have to decide whether it's false alarm or actually there's smoke. So in that also you would use information theory. So there are more applications in other fields, but we won't be discussing any of those in this class. We will start out with the so before we So before actually coming to these questions of ultimate limit of data compression and ultimate rate of communication, first I'll give you a few definitions and results. So, and you'll just have to trust me that these definitions and results will be used later to actually answer the questions that we want. So it's kind of like how you study modular arithmetic in class 10, but at that point of time, there are not many applications for it. But then if you come into coding theory, then modular arithmetic will actually be used. So right now, I'll give you a bunch of definitions and results and prove a lot of theorems, but uh, and they will be used in the end to answer the two main questions. So the things that we'll be talking about will be entropy, mutual information, and relative entropy. So entropy, in some sense, it's a entropy would be a function of a probability distribution. Okay, I forgot to mention the prerequisites for this course, but you should know undergraduate level probability. Should have taken a course. Should know random variables and probability distributions and all that. Otherwise, it will be hard to understand a lot of the things in the course. So once you have a probability distribution, the entropy is a function of the probability distribution. And this quantity that we call entropy, which I'll define later, has some properties that will match with what you would intuitively call information. And the second quantity, mutual information, is will give you a measure of how much information about one random variable is contained in another random variable. For example, if you're uh, talking over the phone, then there will be some input that will go through a channel and that will be received by the receiver. But in between, there might be some noise. So, what exactly is sent by the sender is not exactly the same as what is received by the receiver. But still, there will be some information. Whatever you get at the receiver side, there will be some information which is common to what is sent by the sender. So, that is measured by something called mutual information. And the so the mutual information gives you the information about one random variable contained in another. But if you take it as the same random variable instead of two different random variables, then that would be your entropy. So entropy you could think of as the information about a random variable that it contains. So in some sense you could call it self information. And the third quantity is called relative entropy, which will give you as some kind of measure of the distance between two probability distributions. So if you have two different distributions, how close are they? We'll see that later, but that is kind of what a relative entropy is. So that's why it's called relative. It's the distribution relative to some other variable. So in this lecture, I will only talk about entropy first, and we'll go to mutual information and relative entropy in the next lecture. First is entropy. So this is a measure of uncertainty. So here I started out saying information is the reduction in uncertainty. So that uncertainty is measured by a quantity called the entropy. So you could say information is also the reduction in entropy. Now the definition for this is, so first you start out with the experiment, some random experiment. So there will be a set of outcomes for that experiment, which you would call sample space in probability. Each of each event in the experiment will have some probability, and that will be given by the probability distribution. Then you define a random variable for that experiment. So let x be a discrete random variable. So by discrete, we mean that you are taking only discrete values. Um, you can define entropy for continuous random variables also, and then you can show that you can unify those two things under one definition. But for now, as long as we don't need it, we won't use continuous random variables. We'll define for discrete random variables. So let x be a discrete random variable with alphabet x, alphabet script x. So the random variable capital X can take any value uh, within script X depending on the outcome of the experiment. And probability mass function P of X. So some people call it, some people call this P, denote this by Px of X, where the random variable is written as a subscript. But as long as the context is understood, it's fine. You can write only P of X. And this will be the probability of the event random variable takes on the value X, where small x is some value in the alphabet. So I hope you are comfortable with these things. Have you taken a probability course? Uh, then it's fine. So, so to define entropy, entropy is defined on probability distributions. So first you need to have a probability distribution. You can't, okay. So there is a random variable x which takes values in the alphabet script x, and there's a probability mass function p of x, which is the probability that probability of the event x takes the value small x. So given this probability distribution, we'll define, so the entropy h of the random variable x as this quantity summation negative of summation p of x log p of x, which you can also write as p of x log 1 over p of x belong to script x. So that is how you define entropy. You can also uh, denote this by HFP, where because this depends on the probability distribution. So it only depends on the probability values and not what you call the random variable. So if two different random variables have the same probability distribution, they will have the same entropy. So the main thing that decides the value of the entropy is the probability distribution and not the random variable. So you could call it HFP, where P is a probability distribution. And this, yes. So the unit will depend on the base of this logarithm. So if the log to base 2, then the unit is called a bit. If so for E it is called a nat, and for 2 it is called a bit. Uh, for 10 I don't remember, but mostly we'll be using bits because we are working with information, and most of the time we'll be representing any information with a sequence of binary numbers, binary digits. So bits will be it will kind of give a physical sense to what it exactly means. Right. So for example, let's say you have a you have a coin, and your experiment is you're tossing the coin and you're recording the value of the coin toss, heads or tails. So your sample space is head or tail, and let's say the random variable is also it's just the identity function. So heads or tails. If you get a head, you'll call the outcome a head, and if you get a tail, its value is t. Now, if it's a fair coin, then the probability that x takes the value head is p of h, I could say, is half, which is also be equal to p of t. So the entropy of this random variable h of x is p of h log 1 over p of h plus p of t log 1 over p of t. If I take the log to base 2, it will be half log 2 to base 2 plus half log 2 to base 2. And log 2 to base 2 is 1. So it will be half plus half, which will be 1. The unit will be bit. So you could interpret this as saying to represent the two outcomes, heads and tails, you will need at least one bit. So that could be, uh, so you could say head is 0 and tail is 1. So in this way, you could represent it in a as a binary sequence using only one bit, right? So and yes, huh, yes. So if it's just a single coin toss, right? Then it won't matter. Uh, if you want to record the value of a single coin toss, then you can record it with one bit always. So it doesn't matter at all. So and it doesn't matter whether the coin is fair or not fair, right? Regardless of the probability value, uh, if it could be an unfair coin. The heads has probability three-fourths and tails has probability one-fourth. If it's a single coin toss, it doesn't matter. You can represent it one bit. Okay. Uh, let's say instead of a coin toss, you have a four-sided die, so a tetrahedral die, and the outcome is the outcome on the top face of that die or the bottom face of that die. Like for example, some experiment has the random variable x, which can take four different values. Okay, and then the probability distribution here is p of x. This is the x value. This is p of x. It can take 1, 2, 3, and 4. It takes 1 with the probability half, 2 with the probability one fourth, 3 with the probability one eighth, and 4 with the probability one eighth. So how would you represent this, in your opinion? Okay, that will give you that value, but what is the use of that value? What does it tell you? Yeah. So instead of the information contained in the information, uh, Yeah, yeah. So it will give you the average number of bits. The entropy will give you the average number of bits you will need to represent. mm, the If you represent a long sequence of these numbers, on average, what's the best you can do? Something like that. Huh. So the why we have this definition, right? There are two different ways. The thing is, in some courses, they'll give you the definition and then they will give you motivating examples of why this definition is useful and why this definition corresponds with your intuitive notion of what information should be and how it should be. Right? So I won't give you the exact, in this course, I won't tell you the exact reason why h of x is this particular quantity. In some courses, they do go into that, and that is based on a few axioms. So information is, you'll have some intuitive notion of information, right? And you'll lay down some axioms. You'll say information is a quantity that will satisfy all these axioms. So there are four axioms, and you'll say any quantity that agrees with these four axioms is called an information, is a measure of information or measure of uncertainty. And you will use those axioms to prove that only this function, this p of x log 1 over p of x, only this function satisfies all those four axioms, and no other function would satisfy them. That's why you can unambiguously define h of x as this quantity. What those four axioms are and how you'll use those four axioms, I won't cover in this course. Yes, they'll give you what is the average number of bits you would need to represent each symbol if you have a long sequence, and what's the best you could do in that sense. So, see here what we did in the coin toss example, you had two outcomes, heads and tails, right? You said I will assign 0 to heads and 1 to tail, and using only one bit, I can tell whether the outcome is a head or a tail, right? To represent the outcome. And when you calculated the entropy, it turned out to be one bit, right? So, for analogously, what will you do in this case? There are four outcomes. What would you do? No, no, forget about the calculation. See, heads I represented using 0, tails I represented using 1, right? Right now, we are trying to represent the outcomes of the experiment using a sequence of binary numbers or a sequence of bits. Ah. Yes. Lesser number of bits. Yeah. So that's the use of entropy. It will tell you on average what's the best you can do. You can't represent um, can't have a better representation than that. You can't have a lower than it. It'll give you some bound on uh, how many bits you will need to represent each of the symbols on average. So let's say you have so this x gives you the four possible x can take four possible values. Let's say you represent each of the four possible values uniformly by 2 bits each. Like here you did 1 bit each because there are two outcomes. Since here you have four outcomes, 2 bits each, you can use that and represent. You could say one is 0, 0, 2 I'll represent using 0, 1, 3 I'll represent using 1, 1, and 4 I'll represent, sorry, 3 I'll represent it with 1, 0, and 4 I'll represent it with 1, 1. So now you have used 2 bits to do this. But the thing is, suppose you have n symbols, n values, or you could say n trials of the experiment. So you repeat the experiment n times. Each time there will be a different value for the random variable. The random variable will take a different value. So if you take this as tossing a tetrahedral die, then if you toss it n times, you will get n different values for the random variable. So in n trials, uh, if you represent the outcome of each trial by 2 bits, like how we have done, so uh, number of bits you will require in this case will be 2 into n, right? So you will need to use 2 into capital N bits to represent the outcome of n trials in this representation. But suppose I represent 1 by the symbol 0, I represent 2 by the symbol 1, 1, I represent 3 by the symbol 1, 0, 0, and I represent 4 by the symbol 1, 0, 1, right? So now out of the n trials, again, since 1 has the probability half, so 1 occurs half the time. Of course, it might not be exact in a real experiment, but if it's ideal, then out of n trials, n over 2 trials would have the outcome 1, right? And since the probability of getting a 2 is 1/4, n over 4 of these trials would have value 2. So from this probability distribution, you could say half the trials uh, x is equal to 1, 1/4 of the trials x is equal to 2, and 1/8 of the number of trials x is equal to 3, or and 1/8 of the trials x is equal to 4. So since half the time you get x is equal to 1, and each time you are representing 1 using only 1 bit, right? So in n trials, you'll use n by 2 bits to represent all the ones. There will be n by 2 number of ones. So you'll use 1 bit each time. So you have total number of bits is n over 2, and n by 4 of the outcomes are x is equal to 2, which you will be representing using 2 bits, 1, 1. So the total number of bits used is 2 times n over 4. And uh, n over of n by 8 of the trials, the outcome will be x is equal to 3. And for each of them, you'll be representing using 3 bits. So the number of bits is 3 into n over 8. And the same for x is equal to 4. X is equal to 4 will occur n by 8 times. And each time you'll use 3 bits to represent it. So now the total number of bits you have used is n times half plus 3 over 4. This is 1.75 times n, which is less than 2n, right? So, so earlier you had represented each of the outcome with 2 bits. So in n trials you needed to 2 times n bits to represent the outcomes of each of the trial. But by using a coding scheme like this of variable length, where you represent 1 using a single bit, 2 using 2 bits, and 3 and 4 using 3 bits. So even though you used more number of bits to represent 3, since the value 3 occurs less number of times, overall on average you used lesser number of bits to to represent the outcome of the same number of trials. So here also you had n trials, here also you had n trials. Let's say you get the same outcome with different representations, you need different number of bits, right? So the entropy will leave you this number. Yes. What is it? Yes, you'll say that it's the average length, average number of bits you need to represent the outcomes of the experiment. Yes, that's how you interpret it. On average, you need 1.5 bits per symbol. Uh, you you can do that, but that's a much harder problem, right? See how many words are there compared to the number of letters. There are only 26 letters, so only need to do encoding for 26 letters, right? But if you are doing encoding on words instead of letters, how many words are there in English language? For the entire dictionary, you have to be able to differentiate between each of the words, right? So you'll have to give a unique code word to all the words. That will be thousands, right? Uh, ah, you can do it in the end, but still that increases the complexity of the algorithm. You can do it. Like physically, it is possible, but that is just more complicated. That's all. To actually implement it, right? At the end of the day, you want to use this information. Information theoretic perspective, what you are saying is right. Uh, you might have a different, of course, you'll have to calculate for that also what is the average number of bits that you'll use in the end to represent the same information if you do it on words instead of the letters. But implementing it would be harder on a computer or a communication system. If you want to do that, then the coding part will be hard. So that is something called the encoder and decoder complexity, right? That complexity will be too high if you want to do it on the words. That's why you don't do it on the words. Okay. Same thing with uh, this type of thing happens in a lot of places, not just here, where you might have something that's actually better. Uh, for example, for communication, people use turbo codes uh, for your wireless phone when you're talking on a phone and all, right? People use turbo codes. So for using turbo codes, there's a certain set of software and hardware and all that's already installed on your phones and routers, maybe at the base station. Everywhere, this hardware and software is present. Now, if some other code, let's say you come up with some other code that is slightly better than turbo codes, people will still not implement your code because the hardware is already there for turbo codes. And now, if you want to change this to some other code, you'll have to change a lot of hardware and software. So it might not be worth the gains. So when you have even in semiconductors, when you are doing when you're using some process to manufacture a chip, and you already have a plant for that particular type of process. Now, suppose you invent a new process that will marginally yield better output, then the manufacturer might not actually want to change all his equipment, right? So that marginal improvements might not be useful, and it might be very hard to do it because if the entire plant or manufacturing hub is built around one particular process, then overhaul it entirely to get a new thing, it will be very expensive. So unless there is significant improvement, they won't change anything. They will keep using the same process, even if there's some other that's actually a little bit better. So you could say the same for this compression also. Doing coding on the words is much harder and much more expensive complexity wise than doing it on the letters. So even if there are gains, unless it's a huge amount of gain, nobody will care. All right. So one more example, which is taken from this textbook, is this. So another example. So x takes the value a of probability half, X takes the value B with probability 1 over 4, takes the value C with probability 1 over 8. So it's this same example. So let's just continue it. So we didn't actually calculate the entropy directly here. Right? We didn't use a formula to calculate the entropy. The entropy in this example will be half P of 1 is half log 2. I won't write the base. Uh, Most of the course we'll be using base 2, and 1 over 4 log 4 plus 1 over 8 log 8 plus 1 over 8 log 8. Also note that if you're using p of x log 1 over x, then there's no minus sign, because log of a is minus log 1 over a. So here the minus sign, I have taken it inside and put it, change the log. So if you do log p log 1 over p, then you don't need the minus sign. If you're doing p log p, then you need the minus sign. And this quantity will be half plus log 4 is 2, 2 over 4 plus log 8 is 3, 3 over 8 plus 3 over 8, which will be 1.75. So that's the entropy. So this kind of gives you the minimum average length you would need to represent a symbol. Now, another way you could think of this is, suppose I want to find the uh, outcome of the experiment, and there is someone who knows what the outcome is, but they're only willing to answer with yes no questions, yes no answers. So you could ask a question. For example, you could ask, is x is equal to 1? And they will give you, they'll either say yes or no. If they say yes, then you know the answer, it is 1. If they say no, then you will have to ask another question. You will ask, is x is equal to 2? Then they'll say yes or no. If it's yes, it's 2. Otherwise, they will ask, is x is equal to 3? The answer will be yes or no. If it's yes, it's 3. If it's no, then you can stop, it's 4. So you'll at most have to ask 3 questions to find the outcome of the experiment. Now, on average, how many questions would you have to ask? So you have, so if n is the number of yes no questions, and p of n is the probability that you'll have to ask that many number of questions, you might need 1 or 2 or 3. So the probability that you will ask only one question is the probability that these questions are fixed. So the first question is x is equal to 1. The second question is, sorry, is x is equal to 1. The second question is x, again, it says x is equal to 2. And third question is x is equal to 3. Um, Now, Uh, what is the probability that you'll ask only one question? That is, you'll stop. You'll ask is x is equal to 1 and then you'll stop. What's the probability? The probability is same as the probability that x is actually, if x is actually 1, then you'll have only one question, right? So the probability is half. It is the same as probability that x is equal to 1. In that case, you'll ask only one question. Suppose if x is equal to 2, then you'll have to ask two questions. So number of questions will be 2. The probability of that is the same as the probability that x is equal to 2. So you'll ask two questions with probability 1 over 4. Now if x is equal to 3 or 4, then you'll ask three questions. So the probability that you'll ask three questions is the same as probability that x is equal to 3 or 4, which is 1 over 8 plus 1 over 8. This is 1 over 4. So on average, the number of questions that you need to ask is 1 times half plus 2 times the, let's say that's the expected value, 2 times 1 over 4 plus 3 times 1 over 4, which is 1.75 again. So the uh, minimum expected number of binary questions that you could ask to determine the outcome of the experiment will lie between h of x and h of x plus 1. This we'll see in a later lecture. So this entropy will give you kind of a bound on the minimum number of yes/no questions that you need to ask to get the outcome. Yes, yes, yes. You can think of it that way. So you could say it's a entropy can be thought of or interpreted as the expected value of this self-referential function of variable log of 1 over p of x. And h of x will be ep log of 1 over p of x. Where by ep I mean the distribution of this variable is p of x. So that's one way to think of it. And in many of the theorems, you can use this to simplify your proofs. Instead of writing out p of x log p of x, if you write it as the expected value, you can use all the properties of expectation function. So the sum of expected values is uh, the expected value of a sum is equal to the sum of the expected values. Such type of things you can use it, and it might be simpler to prove some of the theorems or lemmas and all. Okay, what else is left? So we'll just two or three simple lemmas. So first lemma is h of x. Call it, so I'm following the textbook Elements of Information Theory by Cover and Thomas. That's one of the standard textbooks that people use. Um, of course, there'll be lots of textbooks, and different people use different things, but this is one of them. Yeah, what is it? Um, see, lecture notes. You can refer to lecture notes by John Massey. That's what one of my professors used. If you want, I can share. Okay, I'll share on that uh, Moodle platform, whatever it is. Yeah, I'll also upload the lectures on YouTube and embed it in that platform. Yeah. So this is the notes that one of the professors use in IIC. It's a bit, there are no problems or anything as such in this. So it's just a theory there. And the some of the topics might be a bit different from what I'm going to teach, and they might be in different orders, and some of the notations might be different. Rather than that, this is also good. Yeah. So chapter 8, no, chapter 6, I won't be covering. Uh, I'll see out of the remaining 5 chapters, I'll see how much I can cover. To actually cover that much, I'll probably need a lot of time. And this lecture series is only for a few weeks, so I won't be able to cover as much. Yeah, if you are interested, I will do it. Otherwise, probably from next time, I won't be teaching any more courses on IEEE. Yeah, but uh, by the end of the course, if you're still interested, I'll do. I'll probably, yeah, the aim of this part one is first 3 chapters, and part two is the remaining 2 chapters. Uh, Sixth chapter I want to. So I'll try to cover it. Okay, then we'll see if this takes a lot of time, then I won't do any problem solving. You can solve problems from current Thomas textbook. You will probably be able to find solution manuals online also, where you can verify. And if you don't understand any problem, then you can ask me. Okay, so I'll finish this section 2.1 with a few more remarks, and that will be it for this lecture. First thing is this lemma. I'll follow the same labeling as the textbook so that if you want to go to the text and see some of the things, you can follow the same numbering. So first lemma is that entropy is non-negative, and proof is very simple. This is because p of x is between 0 and 1. So log of p of x is a negative quantity. So it's less than 0. So minus log p of x is greater than or equal to 0. That means p of x log p of x uh, is greater than equal to 0 for all x in the script. So the summation is also positive. So the entropy is a non-negative quantity. So it doesn't make any sense to say that average length of the shortest code word or shortest description is a negative quantity, right? You need at least 1 bit to represent any type of information, at least. Uh, you can't represent information with, it doesn't make sense to say that you can represent information with minus 1 bits or something. And that's the first lemma. Second lemma is uh, you can convert from one base to another HB of x. HB of x, we mean we are using a log to base b in the formula. It will be equal to log a base b times h a of x. And this is simply because the log has that property. Log b to base b will be equal to log a to base b times log p to base a. So you can use this in the formula and you will get hb of x is equal to log a base b times ha of x. So that gives you a formula to convert from one base to the other. And the last thing is this section is suppose you have a random variable that takes a value 1 with probability p, takes a value 0 with probability 1 minus p. So, for example, a coin toss, which is not a fair coin toss. So, say the probability that it lands on heads is p, and the probability that it lands on tails is 1 minus p. Then this h of x is minus p log p minus 1 minus p log 1 minus p. And this is a quantity that is used in many places. So specifically for this particular distribution, you define it, you give a definition, call it h of p. It's called the binary entropy function or something like that. So there are two values. Then to satisfy the probability axioms, so both the probabilities must be between 0 and 1, and one of the probabilities is P, the other has to be 1 minus P. So this quantity HFP will come up in many places. So you'll give it a special significance. And this HFP will look, the graph of that will look something like this. Where here it's the P value, and here HFP value. So it takes the maximum when probability is half. That is, if it's a fair coin toss, then the uncertainty in the outcome is maximum, right? You don't know whether it could be heads or tails, and with equal probability. And HFP will be 0 if P is 1. So if it's always heads or if it's always tails, then also there is no uncertainty at all. So HFP will be 0. So this kind of gives you an intuitive, this kind of matches with your intuition, right? The uncertainty of an outcome of a coin toss, it should be 0 uh, if the probability that of heads or tails is 1 all the time. And it should be maximum when they are equiprobable. And this definition of entropy matches with that intuitive notion. So in this particular course, and in one of the courses taught at IIC, that's how we justify the definitions of all these things. Through the usefulness of the things, we will say that this is why we are defining it. In some of the other courses, even in IIC itself, we'll actually prove these, get the formulas for these things using some of the axioms. For example, in a digital communication course, the uh, axioms will be given, and from the axiom, you derive the entropy function. Okay, that's it for today's lecture. In the next lecture, we'll see joint entropy, conditional entropy, and other quantities. Any questions? Okay. I will see you next Wednesday. Bye. Good night.